All right, so in this video, we're going to talk about the logistic function, which is the 12th basic function your textbook includes, which in my opinion is not a basic function. There's nothing basic about this, apart from the fact that it is a very important function in modeling real-world things. So you will see functions with this general form very frequently in real life. So for this one, again, without a calculator, I would not expect you to be able to compute and know what -3, -2, or 1 are without a calculator. So those I'm going to hand to you. I would expect you to be able to plug 0 into this without a calculator, because e to the 0 is 1, and 1 plus 1 is 2, and 1 over 2 is 1/2. And truth be told, if you can plot that point 0, 1/2, and then you can think about what is happening in the end behavior and recognize that there is a horizontal asymptote up here at y equals 1 and a horizontal asymptote down here at y equals -0. Those three things are enough to sketch yourself a pretty accurate logistic function. So the logistic function, let's think about it. What values of x are you allowed to plug in? Everything. Your domain is all real numbers. Your range is bounded. It is limited. Yes, it is bounded. Above by 1 and below by 0. And you never actually get to 1 or 0. So again, how do we know that that's the range? Well, the end behavior we want to look at, right? We want to look at limits. So if I were to look at the limit as x goes to infinity of my function 1 over 1 plus e to the -x. It might be helpful to remember, I'm going to rewrite this, limit as x goes to infinity of 1 over 1 plus, well, e to the -x, that's the same thing as 1 over e to the x. So now think about it. When you plug infinity into a denominator, e to the infinity is going to be an infinitely big number. 1 over a really, really big number, well, 1 over a really, really big number, this whole thing essentially is approaching 0. So this limit is really kind of approaching 1 over 1 plus something so small it doesn't even matter. That's the same thing as 1 over 1 is 1. So that's my end behavior as x goes to positive infinity. I get the horizontal asymptote y equals 1. That's my right behavior, right? As x goes to positive infinity, y goes to positive 1. So again, y equals 1 is the equation of my horizontal asymptote. For the left direction, right, the limit as x goes to infinity of 1 over 1 plus e to the -x equals, well, sorry, negative infinity. So think of this. If you're approaching negative infinity, well, negative times a negative, if you're plugging in a really, really big negative number here, negative times a negative is a positive. So this is e to some positive exponent. Well, e to some positive exponent, let me write this out. I'm going to do kind of like a squiggle. So this is like 1 over 1 plus e to the positive infinity. Okay, this is an abusive notation, right? Because it doesn't ever equal e to the infinity. But e to the infinity, that's kind of like 1 plus a really big number, right? And 1 plus a really big number is still a really big number, right? So what's 1 over an infinity? Again, that's the whole thing, this fraction, right? It all goes to 0 because 1 over a really, really big number is really small. So this whole limit here equals 0. And hence we get our left-sided horizontal asymptote. Our left end behavior. As x goes to negative infinity, y goes to 0. All right, so let's look at some of the properties again. So is it continuous? Yes, it's continuous for every real number. It's continuous on its entire domain, and it's increasing on its entire domain. It's never decreasing. There's no symmetry because it doesn't go through the origin, so it can't be odd. If you flip it, it's not even. It is bounded. And yet, because of these strict inequalities, because it never actually equals 0 or never actually equals 1, there isn't a maximum or a minimum. There's none. There are no vertical asymptotes, but the horizontal asymptotes are absolutely crucial in understanding the way this graph works. Okay, so that's your logistic function, 1 over 1 plus e to the negative x. Let's now look at the greatest integer functions. So when I write bracket x, or what I'll often write is int x, right? This is the integer. You can almost think of it as the integer part of a number, but saying it like that is misleading when we talk about negative numbers. So start with positive numbers first. If I wanted you to tell me what's the integer part of 2.5, well, you'd say, oh, hey, that's 2, right? And in fact, 2 is the greatest integer less than or equal to my x value of 2.5, right? So 2.5, what integers are less than 2.5? Well, 2 is less than 2.5, 1 is less than 2.5, 0 is less than 2.5, but 2 is the greatest whole number integer that is still less than 2.5. All right, so that's what this less than x means. So if we were to look at my table, oh, I didn't even have it. Well, okay. 1.5, what is the smallest integer, or sorry, what is the greatest integer that's still smaller than 1.5? Well, that's going to be 1. How about 1? Well, 1 is equal to 1. So at 1, 1, I've got a solid dot. At a half, 1 and a half, I've got 1. What about 2? Well, at 2, the greatest integer still less than or equal to 2 is 2, so I've got 2 here. What about 1.9? Again, what's the integer part of 1.9? It's 1. So I've got a solid line leading all the way up, but then I'm going to have a hole there, and it's going to jump up to 2, right? 2.5, that's what we did before. The integer part of 2.5 is 2. Right, and you can see what I'm going to end up having is all the way up until 3, I'm going to have a hole, then I'm going to jump up to 3. And then all the way to 4, and then I'm going to have a hole. And rather than continuing drawing this, I can go dot, 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 and that means same pattern heading up in that direction. Okay, now again, I don't really like calling it the integer part of a number because it is misleading when you get to negative numbers. So 0.5. Well, the integer part of that is 0, 0, 0. So even still, hole there, solid line. But what about negative 0.5? Negative 0.5, this is where we actually have to use the definition of the greatest integer function. This is why it's called the greatest integer function. If I'm looking at negative 0.5, that needs to be what number is less than or equal to negative 0.5? That is a integer. Is 0 less than negative a half? No. But negative 1 sure is. Right? Negative 2 is, so is negative 3. But negative 1 is the greatest, right? The greatest such integer that is still less than or equal to my x value. So negative 1/2 actually gets plotted down here at negative 1. Negative 1, clearly negative 1. Negative 1.5, that's going to be negative 2, right? So open dot, solid line, dot here, right? Negative 1.5, that's gets plotted down to negative 2. Negative 2 is going to be negative 2, right? And so we see we've got this same, I'm going to go dot, dot, dot to indicate same pattern. So it's this step function. So the greatest integer function, if you're talking about positive numbers, just think it's the integer part. If you're talking about negative numbers, you have to think what integer is less than this negative number, right? So negative 1.5, negative 2 is the integer less than negative 1.5, right? So what is the domain of this function? Well, the domain of this function is all real numbers. You can plug anything in here, right? What's the range? So when I look at what y values are allowed, so 1's allowed, 2's allowed, 3's allowed, negative 1, negative 2. So it's all of the integers. So bold Z is the set of all integers. All right, so If you ever see a bold Z, it's because it's from a different language, blah, 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 set of all integers. Okay, so my range is the set of all integers. So another interesting thing about this function, is it continuous? Well, overall, no, it's not continuous. It has an infinite number of these jump discontinuities, but it's continuous on these little teeny tiny intervals. So again, where is it continuous? Well, it's continuous on all these little tiny intervals, but overall, it's very discontinuous, right? It's got an infinite number of jump discontinuities. Is it increasing? And where is this function increasing? Well, it's really only increasing at every jump. So overall, yeah, it's increasing overall, but it's mostly constant on all these little tiny intervals. So this is a special function in terms of describing where it's increasing or not. Is it decreasing? Never. Is it symmetric? None. All right, and so is it bounded? No, right? It's going up infinitely and down infinitely. Max and mins? None. Right? Vertical asymptotes? None. Horizontal asymptotes? None. And so the end behavior, right, as x goes to positive infinity, y is eventually stepping up to positive infinity-ish as well. And as x goes to negative infinity, again, my y values are getting negative and more and more and more negative. So the end behavior is running towards positive and negative infinity. So that's our greatest integer function.